Sits. Okay, let us start. For our first lecture of today, we are happy to have Roberto Emparan with his course on physics of near-extremal black holes.
Thank you. Can you hear me? Yes. Okay, so any questions about what we saw last day? Yeah, well, something that I didn't do, I forgot to do, is to give you references. They are already in the notes that I sent last night. So, yes? If I know, maybe what I can do is, yeah. But maybe something that I can do is move this farther up. Is it better now? Marginally? So, I don't know if there's a volume. Yeah, probably they have to do it. Yes. Okay, maybe I can try to speak a little louder. Yeah, okay. So, yeah, so references, if there's one reference that you want to follow, there's a single reference, then it should be this paper by Luca Eliasio and Joaquin Turiazi. Luca and Joaquin are the heroes of this story. There are many people who have worked on this, but this paper that they wrote a few years ago on the statistical mechanics of near-extremal black holes, in the non-BPS case, I think it's a fantastic paper. It's a great paper, okay? Then other things that I will be discussing about for the interaction of these black holes with radiation, there was this paper by Brown, Eliasio, Pennington, and Usatiuk, which is a very, well, here I think there's a T, it shouldn't be a T. I don't know why I wrote a T. That's a 7. Okay, so that's a paper on, it's a long paper with lots of details about emission of radiation. Then this is a short paper that I wrote about the absorption and scattering of radiation. And there are a couple of reviews. This is a long and detailed review on JT gravity, and this is more of a more impressionistic summary of recent developments on near-extremal black hole physics. Okay. Now, the other day, one thing that we saw, one of the last things that we saw, is that the energy of a black hole, near-extremal black hole, the energy, when you expand it for small temperatures, so this is the energy above the extremal bound state, this mx, this is the charge for a Rasnostrom black hole. This energy took the form, this form is something that's quadratic in the temperature. This is a constant. This has the dimensions of inverse of an energy, and it depends on something that's something that we're calling like this, and this energy scale, this is something like Q cubed, okay, in Planck units. So what I want to emphasize is that this quadratic dependence on the temperature, that's very general for black holes near extremality. Okay, we derived it for the Rasnostrom solution. You can derive it more generally for any black hole that has an ADS2 throat, as we will see. And it's also valid for, say, for near-extremal Kerr, even if in that case the near-horizon geometry is more complicated. Okay. So this is one of the main features of these black holes, and it will be appearing once and again in the lectures. Okay. In the notes, there was something that I included, but I'm not going to have time to cover, which is super radiance and pair production. Maybe if at the end of the lectures we still have time, then maybe I will mention something about it. I don't know whether I will also have time to talk about, I said that, well, my plan was to cover the Aritaxis instability and other properties of extremal black holes, but we will see how far we can get. And we don't have to get to that. What I want to cover is quantum physics of near-extremal black holes. That's the main goal. Anything else that we can cover, of course, it will be better, but if not, doesn't really matter much. So we took the Reis-Nostrum solution, we computed thermodynamics, then we expanded it near extremality. We found that result. What we're going to do is to see what happens to the geometry in this near extremal limit, whether we can find a simpler form for the geometry. And that's what we're going to do now. Okay? So the black hole was characterized by the mass and the charge. When they are equal, we have the extremal limit. We're going to take now a limit which is similar to the one that we took the other day. So we were expanding for m almost equal to q. This is a small number. We were calling it epsilon squared. Now I'm calling it slightly differently because I also want to change the coordinates. But if we do this, then the radii of the inner and outer horizons are what we want to do is to take this parameter lambda to 0, keeping mu fixed. Okay? But we're also going to scale the coordinates so that we go close to the horizon. Okay? So as we keep this new coordinate row fixed, can you hear me? Is it okay? Yeah, because I don't know. Yeah, sometimes I hear some reverb. Sometimes I don't. So we're going to introduce going from the coordinate r to the coordinate rho, keeping rho fixed when lambda goes to 0. And we also have to rescale the time coordinate. What this means is that we're going close to the horizon, and then this means that we rescale in time by the redshift factor, because there's a large redshift close to the horizon, and this rescaling accounts for that. Okay? And this means that, yes, yeah, there's something about it.
No, the microphone, I just have to,
yeah.
Can we put it in, like, right in the center? There we go.
Okay. Okay, so it's in the gauge field. Can you hear it? Can you hear me? Yeah, okay. Okay, so we have this. Now we take the geometry that we wrote the other day. Take this and expand it for small lambda. So what we find, the geometry becomes keeping this term for reasons that will become apparent in a moment. Okay? Now, the geometry takes, well, it was already factorized in this form, but let's focus on this part of the geometry. You can verify, you can compute, say, curvature invariance. We're going to see it, well, it's easy to see explicitly that this is a geometry of a constant negative curvature. This means that this is anti-de Sitter space in 2 dimensions. Okay? The gauge field, by the way, it's also, we're not going to use it much, but it's minus q over r, and then in the limit, this becomes minus 1 plus 1 over q lambda rho. Okay? Now, when we rescale the time, I mean, this is a constant, so we can gauge it away. When we rescale time, this lambda will disappear. Okay? So this is ADS2, and it's ADS2 for all values of mu. The role of the parameter mu here is to allow me to be not quite at extremality. Okay? I can be away from extremality if I keep mu different than 0. Okay. So as I said, this has the curvature of this is minus 2 over q squared. And very often I will, instead of using q, I will write L, which is the radius of the ADS2, and it's also a radius of the sphere. Okay? Now, geometries of the form, the solution of Einstein-Maxwell, which is ADS2 cross S2, it's sometimes called, and in the past it was more often called, the Bertotti-Robinson universe. Okay? If you hear Bertotti-Robinson, it's this geometry. Now, let's examine what the geometry is for different values of mu. So for mu equals 0, this is the extremal limit. This is the limit where the two horizons are equal, r plus and r minus. And you see that here the horizon at rho equals 0, that's a double root. The geometry is okay. Just write in the two-dimensional part. Very often you will see this expressed, which you can change the coordinate rho for its inverse. You want it to keep dimensions of length, then you introduce the factor of q squared. To many of you, this will be familiar as the Poincaré patch of ADS2. If this were Euclidean, this would be the form of the upper half plane, the Poincaré upper half plane. Okay, so this we call Poincaré coordinates for ADS2. Those of you who are familiar with Penrose diagrams, you know that this is the part of the geometry that's covered by these coordinates. The boundary is at z equals 0. This is where the metric blows up. At rho equals infinity, the metric blows up. This is the Poincaré horizon, which is at rho equals 0 or c equals infinity. Okay? So one often jumps between these two sorts of coordinates. Okay? So that is the extremal limit. Let's see what happens when mu is different than 0. When mu is non-zero, then we can always rescale it to be +1 or -1. We can rescale coordinates, we can rescale rho, and we can rescale the time coordinates so that we can make mu equals 1. Okay? For this, what you have to do is rescale rho and okay. So then mu becomes a sign. When mu is positive, we can set it to 1. I will keep it. Okay, I won't rescale it, but then we see that we have a horizon at rho h equals square root of mu. This is where the GTT term vanishes. In this case, what we get is what's known as Rindler ADS2, and sometimes also thermal ADS2, which I don't like so much this terminology because in higher dimensional ADS, this is not what we would call a thermal ADS. But well, this terminology in 2 dimensions, that's fairly common. Okay. So in this case, the geometry you have horizons of finite temperature. This means that they are bifurcate horizons. So they are horizons that have this bifurcation point. The boundary is at rho going to infinity, and the horizon is at this value, okay? And your coordinates only cover this. So this is similar to Rindler space in the relationship between Rindler space and Minkowski space in the asymptotically flat case, the flat case. So this would be, trajectory like this is a trajectory of uniform acceleration. So this is the space that's accessible to observers that move in ADS with a uniform acceleration, okay? And that's why I like to call it a Rindler ADS. Now, in this case, so we had an expression the other day for the temperature. We can compute the temperature directly in the geometry, or we can take the temperature of the Rice-Nordstrom solution and rescale it. If you take the expression for the temperature that we gave the other day, in terms of R plus and R minus and so on, you remember that the temperature was proportional to the difference between R plus and R minus. The difference between R plus and R minus is essentially lambda square root of mu. So this is what we get here. Now, since we rescale in time, then we rescale in all energies, and then the temperature also gets rescaled. So after applying that rescaling of the time coordinate, what we find is that the temperature in the rescale geometry, the near horizon geometry, is 2 pi q squared. Okay. Now, the fact that this temperature is something that, from the point of view of the original solution, is something that would go to 0, then this means that this temperature for asymptotic observers, observers in the asymptotic geometry, this temperature is infinitesimal. Okay? There's the redshift factor near the throat. If we account for the redshift factor, then we get a finite temperature. But for observers far away, the temperature is infinitesimal. Okay? So we've covered the two cases of mu equals 0 and mu positive. The case of mu negative is much less discussed in the literature, but it's nevertheless easily recovered from what we have done. So the case of mu negative, when mu could be rescaled to -1, this would correspond to a case where we have charge larger than mass. So we don't expect to have a horizon, and we don't have a horizon because when mu is negative, this is always positive, so we don't have a horizon. So in this case, the geometry is, let me rescale it to be -1 mu. So in this case, what we find is this is, again, ADS2. You can transform it to any of the other forms of ADS2 that we've seen through a local change of coordinates. But now these are coordinates that don't have any horizon, so they cover ADS2 globally. This is global ADS2. And if this is ADS2, these coordinates cover it globally. Rho equals 0 is the line at the center. And this would be rho going to infinity, and this rho going to -infinity. Okay. You can have a rho going to -infinity here without any problem. Okay. Simplify that. So this is also covered. Then you may wonder, why did I call this near horizon limits when there's no horizon? So this is because these are, this is an abuse of terminology that's widespread. We call these near horizon limits, but they are actually throat limits. Okay? The near horizon limit of a non-extremal solution is actually Rindler space. we get here more than Rindler. So here we're taking a limit that's, we're going close to a horizon in some sense, but not very close. And here we're not even getting close to a horizon because there's no horizon to begin with, okay? So they are more properly throat limits. How should we think of these three limits in terms of the initial Reis-Nostrum geometry? So let me draw Penrose diagrams again. So the Penrose diagram for the non-extremal Reis-Nostrum solution something like this. So this is non-extremal Reis-Nostrum. What we're doing, let's use color, where we're taking the near horizon limit or the throat limit, we're focusing on a region like this, okay, this region over here. This is close to the horizon. And then the boundary are, we can straighten out through a conformal transformation these time-like lines as the boundary, but we're keeping the horizon. So these horizons are retained there. No, sorry, no, this is wrong. Yeah, no, sorry, I'm not doing it right. I'm going to redraw it again, sorry. This is the geometry, and now, well, we're taking near horizon here and near horizon here, okay? So we're retaining this and that. Is this visible at all? Not sure whether this is. So we're retaining this part of the geometry. Okay? These lines, as I said, I can straighten them to vertical lines, and now I'm keeping these horizons. Okay? So the horizon here, this horizon is here, and then I have a repetition of all of this. Okay? You see that the singularities are not visible anymore. The singularities are pushed to infinite distance. This is a region that has constant curvature, so there's no curvature singularity anywhere. Okay? So this is the near horizon limit, it retains this region. For Poincaré, it's similar, the Penrose diagram for Poincaré. This is something that, as I will emphasize later, we shouldn't be really talking about it, but let me go to mesh again. So this is the Penrose diagram of the extremal solution. Now I'm taking the near horizon limit, keeping portions of the geometry. And keeping this, straightening this out, these lines. And then I have these horizons, which look like this. Okay? So this is the near horizon limit, or the throat limit of extremal ADS2. Now, for the case of the global geometry, the global ADS2, we start from a black hole that has mass less than the charge, so that's a naked singularity. In this case, the limit, we're taking it, we're considering here a particular line. It's a line where the function f, where the derivative of the function is 0. This is not a horizon anymore, it's not a horizon. And then we're focusing on a small region around it. Okay? Now when we straighten out these two lines for conformal transformation, then what we get is global ADS2 without any horizon. Okay? And the center, this line corresponds now to rho equals 0. Okay? Yes?
Just a quick question on the last point. This global ADS2 that you get here, that it comes from some regime we're having.
There's another way of getting global ADS2, which you know about, is using wormholes.
That was my question.
Yes.
It's different from this like global ADS2 wormhole construction.
This, yeah, it's different because here I'm just doing Einstein-Maxwell.
Right.
For the wormholes, you need fermions.
Yeah.
You need so you need something that gives you some sort of a negative energy, because that's what in the wormhole you get a negative energy. Here we get negative energy or energy below the extremal bound, so that's what we need. Okay, the negative energy thing that I'm mentioning here is that the sign. You know that the subleading terms in GTT give you the mass in general, right? So it's like when you're considering asymptotic flat geometry, then say in ETS, the subleading term, you have the leading term, subleading terms are telling you about the energy that you have in your system, okay? And the fact that this is negative tells you that you have a positive mass, okay? Now it's very similar here. We have the leading term is rho squared, this is subleading, okay? Whether that's an energy that you have to be careful, but you can think of it heuristically as that this being positive means that you have some positive energy, that in this case is giving you a horizon. Rho equals 0, it's, you have the extremal case, the 0 energy case. And mu negative means that you're at energies below. You have some repulsive effect, okay? And that's something that you can verify in the global geometry. When you go to 0, things can focus and defocus, okay? Even if that's something that you need to consider the behavior of the sphere to see focusing and defocusing. But in a sense, here you have this kind of a negative energy. You're at energies below the other states, okay? And what Alexander was saying is that there's other ways of getting this negative energy effect, which is, for instance, considering a negative energy coming from Casimir energy of fermions when you include the additional sphere. That's another construction. This, by the way, this geometry, you can think of it as a wormhole because it's connecting two disconnected asymptotic regions. Okay? You have these two boundaries, they are disconnected. It's not like in higher ADS, in ADS2, these two are disconnected, and then this geometry connects, and the bulk is connected to separate asymptotic regions. And in that sense, it's a wormhole, and it appears actually as the near horizon geometry of certain wormhole constructions. Okay? But here we're not getting it like this, we're obtaining it just out of Einstein-Maxwell theory. And this is not a wormhole, it's just a funny geometry. The singularity, the naked singularity, it's pushed away to infinity, so we don't see it here. Now, something that I haven't mentioned yet is this term that I was keeping here, okay? That correction, that's something that tells us how the size of the spheres changes. So that's something that tells us how these throat geometries open up and connect to the asymptotically flat region, okay? And, well, we will see that, well, we were writing this, when we were performing the dimensional reduction, we were writing this as phi squared, okay? So in this case, what we would have is that phi is q plus lambda rho, okay? We will write this in a few minutes as a constant value, phi naught, plus a field that we'll call again the dilaton. Okay? This dilaton in all three cases is equal to rho. You may say, well, it's funny that no matter what, whether mu is positive or negative or 0, we get the same dilaton. That's actually not quite the case because the coordinates rho and tau, in each different case, they have different meaning. Okay? Here you see that rho, constant rho are these lines. Here, constant rho are lines that go like this. And here, constant rho are these lines. Okay? So the meaning of the rho coordinate in each case is different. So a line of constant dilaton is different here, than here, and then here. Okay? And that's important. So the non-zero dilaton, when we have this non-zero dilaton, this breaks the equivalence between the three geometries. If we just consider the metrics, they are all diffeomorphism to each other. There's a coordinate transformation taking you from one to the other. But the dilaton would change if you perform that change of coordinates between one and the other. Okay? So the dilaton is breaking the diff symmetry between these geometries, okay? And makes them physically different. Okay? It's the dilaton that makes these three solutions physically different. That's why we were keeping it. Okay? Questions?
I have a question. So here we are taking a near-extremal limit, taking lambda to 0, but we are also focusing on a very specific part of the geometry.
Yes.
For instance, it takes away the singularity.
Yes.
How are we sure that that is the important part of the geometry and we can neglect other
Well,
parts?
because, well, of course, the asymptotically flat part of the geometry, that's important because you want to preserve it. That's where you may be observing things. But we will see that it's in this geometry that you find the dynamics is concentrated. The light modes become dominant over this part of the geometry. You can take other limits of these solutions, but they don't seem to give interesting physics.
So for instance, the region close to the singularity does not lead
The region close to the singularity, okay, good. There's something there. Of course, the singularities are interesting, but it's a different physics that you're capturing if you're going close to the singularity. Well, first of all, the singularities in this, okay, yeah, that's a different thing. So, for instance, we're not going to say much about the inner horizon there, but the singularities here in this part of the geometry, of the near-extremal geometry, of the non-extremal res nostrum, we think that this is unphysical because the inner Cauchy horizons are unstable to a phenomenon called mass inflation. And that seems to be fairly generic. So in a physical situation, when you start with a non-extremal res nostrum, what we expect that the Penrose diagram, instead of being like this, the Penrose diagram is going to be this part that here you say in the maximally extended and literally extended res nostrum geometry, you get this. This is the inner Cauchy horizon. This will be unstable and become a singularity, which may be in part null or in part space-like. So perturbations, the expectation is that typically they are going to grow large over here. If it's not a classical perturbations, quantum effects are going to turn this into a singularity. The back reaction, you can compute the stress energy tensor of classical perturbations or of quantum fields. It diverges over the inner horizon, and the divergence of this stress tensor, expectation is that this is going to create a large back reaction that turns this into a singularity. So this is going to become something like this. So all of this part, we think it's unphysical. This is part of what's known as the strong cosmic censorship conjecture. So all of this, we don't consider in this case physical. And then this is more like the Schwarzschild black hole geometry. So the structure of the singularity here, you may want to study it, or you may want to study the interior, but maybe what you're doing in that case is not very physical, because we think that that's not going to survive. Okay? Then we will also see that for the extremal res nostrum, that the infinite throat and other properties, they are not physical either. So parts beyond this, it's not clear at all that they have any physical relevance. Okay? The exterior, yes, but other parts of the interior, they don't seem to be very physical. I may be wrong, maybe there's something that we will discover that is something else, but so far, I think that these arguments are telling us that that's not very physical. So what we're going to do is physics of the horizon, not physics of the singularity. They are different problems. Both of them are very important and very deep. But I think that it's fair to say that still we understand much better properties of horizons than properties of singularities. Sometimes I like to say that it's a bit like Anna Karenina. Horizons are smooth, happy places, and all happy places are similar to each other. Singularities are unhappy places, and unhappy singularities are all different from each other. And that's one reason that we understand singularities much less. Okay. Of course, singularities and horizons are connected through the cosmic censorship conjectures. I think that that's, well, horizons and singularities are the most important things, or some of the most important things in gravity. The other thing that's important is the universe, cosmology. Okay? So now let's return to the Einstein-Maxwell theory. We're going to see now the relationship between near-extremal black holes and a particular dilaton gravity theory known as Yakif-Teitelbaum theory, JT gravity. Okay. So we're going to return now to this reduction to the S-wave sector, spherical symmetric sector. Recall that the spherical symmetric, the reduction to the spherically symmetric sector, that's something that at the classical level is consistent, it's a consistent truncation. What I mean by this is that solutions of the reduced theory are also solutions of the higher dimensional theory. Okay? That's something at the classical level you can easily prove. At the quantum level, this will not be true. These consistent truncations are a classical thing, and they can be important, but physically, they are not that's super important because quantum physics, for instance, is going to break that. Quantum physics doesn't allow you to decouple sectors easily. Everything will talk to each other. But nevertheless, you can still use the reduction in a way that's still useful if you restrict yourself to low enough energies. That's what we typically do in physics. If you're doing physics, you care about what's the sector that dominates at low energies. Whether the truncation is fully consistent or not, that's a different matter and often not that relevant. Okay. So we found, when we truncated to the spherically symmetric sector, we found that two-dimensional theory of gravity, describing that part of the geometry, this was for a given charge of the black hole. I'm dropping the bars. In the previous lecture, I was putting a bar, an over bar in front of, on top of the metric. I'm dropping that now. This potential of this form. Here there was a length scale, a fiducial length scale, something that I introduced to keep things dimensionally correct. I can choose it at will. The other day I didn't say it, but I'm going to take it to be the natural length scale in the geometry. Okay, that's L equals Q. So by studying this sector, we could obtain the Reis-Nordstrom solution in general, near extremality or not, or far from extremality. The Schwarzschild solution also appeared as part of this by solving the equations of this theory. Now we're going to expand around extremality. Dilaton here, the extremal case is Q squared that we had it. I'm going to do what I said before. I'm going to introduce the deviations away from this value. I'm going to call it field phi, which I take to be much less than Q squared. Okay. So now I go to this limit close to extremality, and then I expand for small values of phi. When I expand this, the action becomes L is Q. This is expansion. The phi gives rise to these two terms, and out of the potential, you get this one. Okay? You remember that these two terms of the potential, this came from the curvature of the sphere, this came from the gauge field, from the F squared, the Maxwell term. Okay? And here now they combine to give me this. Now this part of the action, that's very simple, actually too simple for us. This is a term that's topological. Okay? Because you know that in 2 dimensions, this is giving you the Euler number. Integrated on a 2-dimensional sphere, on a 2-dimensional space. This gives you the Euler number, which is a topological invariant. Okay? So this doesn't have any dynamics, and that's, of course, directly related to the fact that if you vary this term with respect to the metric, then what you get is the Einstein tensor, and the Einstein tensor is identically 0 in 2 dimensions. Okay? So the important part is this term. Okay? That's this term. This is what I'm going to call the JT dilaton gravity theory. Very often I'm going to set L to 1, okay? Just for simplicity, which I can always do. As I say, this is a 2-dimensional, forgetting the dilaton, which is the whole point of all of this game. So this is a theory that has gravity and the dilatons, a dilaton gravity theory, a particular case of the theories that we saw the other day. There are other theories of dilaton gravity that appear also in 2-dimensional black holes quite often. One of them is very similar to this one, but what you find instead of this takes this form, with the phi not multiplying the 2. You have to keep this in mind. This is sometimes called the CGHS theory, which is a misnomer, because it wasn't first found by in the paper, CGHS paper. It was known from before. Sometimes people call it the 2-dimensional string theory action, effective action, which is a better name. Sometimes people call it the Witten theory, which is, again, one of these misattributions that's fairly common. But it's another theory that's important, but we're not going to mention anything. Okay? The difference, as I say, a crucial difference, is on the way that the dilaton couples to the rest of the geometry. Okay? Now, this is the bulk action. This is the two-dimensional part of the action. The other day, somebody asked about the boundary terms, the Gibbons-Hawking-York terms. Okay? The Gibbons-Hawking-York terms, these are terms. By the way, it's 50 years since Gibbons and Hawking wrote their paper, so it's going to be some, it's going to be celebrated in different events. Okay? So the Gibbons-Hawking-York term is a term that appears at the boundary of your geometry, that you introduce at the boundary of your geometry. It was introduced, this is what York was the first one to fully realize, so that you get a properly well-defined variational problem. When you want to vary the action and you want to derive the Einstein equations, you have to keep in mind what kind of boundary conditions you're imposing. If you want to impose Dirichlet boundary conditions for your field, in order for the boundary, for the functional derivative to be well-defined, you have to add a boundary term. So it's a term that allows you to get a properly well-defined variational problem. Okay? That's something that you can do in 4 dimensions. When you begin in 4 dimensions and then you reduce your action to 2 dimensions, then, well, you're also going to inherit a boundary term for this action. Okay? In a sense, we have this picture where we have the asymptotically flat region, we have the throat, where you have here ADS2. You have here the asymptotically flat region. At the boundary of ADS2, these 2 geometries are glued to each other. In order to ensure that you're gluing the asymptotically flat region and the ADS2 region properly, then you have to add a boundary term. Okay? So that's something you can do. You can derive the boundary term that you add to this action by doing this reduction and cutting properly. But a faster way is to start from this theory and derive the Gibbons-Hawking-York term just by requiring that at this level, forgetting about whether there's a connection to a far region or not, then if you want a variational problem for this action to be well defined, then you find that you have to add a boundary term, the Gibbons-Hawking-York term. Okay? The 2 ways of doing it are equivalent. They give you the same result. This one is a bit faster. The other one is a bit more conceptually satisfying, if you want. So then, so this is for the bulk of your manifold. This is the 2-dimensional space. This is going to be a boundary term. That we're going to write in the following manner. So I add to my action this term, and I'm going to unpack what I'm doing. Okay? So this is a boundary term, a term that lives at the asymptotic boundary of my ADS2 geometry. Okay? It's, the boundary is 1-dimensional, so I only have 1 dimension here. It's going to be a time direction, okay, because the boundary is at constant at some large value of the radius. So what remains is the time direction. This thing over here, as I take the dilaton to the boundary, the dilaton will diverge. We saw that the dilaton was proportional to rho, right, in our solutions. So when rho becomes very large, the dilaton is going to diverge. So then what I do is I define I introduce a cutoff at a large value of rho, and I redefine a renormalized value for the dilaton by this at the boundary. Boundary of ADS2, I introduce a cutoff at rho, large values of rho, epsilon is small. So this is what I call the renormalized dilaton. Okay? This is the extrinsic curvature of the boundary. This is the usual Gibbons-Hawking-York term. Okay? So in principle, we wouldn't need this term here. Once you have this, you already have a well-defined variational principle. Okay? So this is the Gibbons-Hawking-York term. What is this? This is not a Gibbons-Hawking-York term. This is what we call a counter term. So this is a term that depends only on the intrinsic geometry. It only depends on H. It doesn't depend on the extrinsic geometry. This is something that's a derivative of the boundary in the radial direction, the normal direction. So this contains extrinsic information of the boundary. This is only dependent on the metric at the boundary, because it doesn't, it's just multiplying the square root of the induced metric at the boundary. So this is, if we vary the equations, if we vary the action to obtain the equations, we vary the action, keeping the boundary metric fixed, then this term wouldn't contribute anything. Okay? So this doesn't modify the classical equations of motion, it doesn't modify the variational principle. Okay? The role of this term is to subtract divergences. Because as we will see, well, we have an infinite space, ADS here, we're extending it to an infinite space. In an infinite space, the action is going to be infinite. It's a non-compact space. Action at the boundary is going to become very large. This is going to give us a divergence contribution to the action. This is also something that's going to diverge, because the metric at the boundary is going to, or the integral of the metric at the boundary, this is going to become very large. But the divergences here and the divergence of this term, they cancel away. This term is introduced so precisely as to cancel divergences. Okay? So the role of this is a counter term, this is not a counter term. Sometimes people call the Gibbons-Hawking-York term a counter term. That's completely wrong. If you're doing that, then you don't know what the Gibbons-Hawking-York term. The Gibbons-Hawking-York term is not a counter term. It's a term that you introduce to get a well-defined variational principle. You introduce it, and divergences are still there, so it's not removing divergences. Okay? What you introduce to remove divergences are terms like this that don't depend on extrinsic curvature, they depend only on intrinsic curvature, on intrinsic geometry. Okay? We will see that this term is right to eliminate divergence. We're going to see it in a moment. Yes?
So, I mean, you are basically choosing a solution which has such property, right? At boundary, it's like this 1 by epsilon diverging.
Yeah, the dilaton in general is going to behave like this. We can solve the equations in general, and they're going to take the dilaton
Particular solutions. But something similar happens in when you study Liouville CFT on the disk, the ZZ boundary condition, that metric diverges as you reach the boundary.
Yes, this is a different gravity theory. It's not Liouville.
Yeah, I was just like, I mean, contrast the two things, like
probably they are
pseudosphere
related,
people
but
call
I
it,
can.
think.
Yeah, probably they are related, but I'm not
Pseudosphere.
sure. I can give you a.
Okay.
But I wouldn't be surprised if there's a relation between the two.
Okay.
I'm not seeing it very clearly now, and I don't want to say things that would be wrong.
I mean, action is completely different, but
It's different. It's a completely different theory, but yeah. Okay. So this is our entire action. We're going to neglect the topological term, because we're going to all the time consider that the topology of the space where we're working is fixed.
Hello,
By the way, there's also going to be, I mean, you can add, and in general you would obtain it, there's also a topological contribution coming from the curvature, okay? And that would add to the Euler number, it would add the contribution from boundary terms. Was there a question?
Yes.
Yes.
Shouldn't the boundary term come with a plus sign? We are in ADS, right?
I think that I got the signs right for Lorentzian signature, but I'm not, I mean, plus and minus signs in my notes.
Okay,
I've tried to be careful, but I may have made mistakes, okay? The final results, they are all right. In the intermediate steps, signs may fluctuate, okay? And so far I'm working in Lorentzian signature. If you're working in Euclidean signature, of course, there are signs that can be different, and it's very common in this context to work in Euclidean signature. Okay. So we have this theory. We can derive equations, if you vary the dilaton, then the equation that you get is that R plus 2 is 0. So the space has to be locally ADS2. Okay? So the geometry is, that part of the equation is very simple because all of our geometries have to ADS2, and that's what we already saw. The other equation, you want the Einstein equation, this is AB, which is this equation is the equation that the stress tensor of the dilaton vanishes. Okay? Because as I said, the two-dimensional Einstein tensor is identically 0. In this case, the equation, we saw it the other day for the general dilaton gravity theory, for this particular dilaton gravity theory. So this is convenient to take to separate the trace equation here. It's simple, and then you can subtract the trace and obtain another geometry. But in general, the equation is this one. Okay. So can we solve these equations? Yes, we already had some solutions. Okay. The solutions that we wrote before. With kappa equals plus minus 1 or 0, and with the dilaton being proportional to rho. These are exact solutions of these geometries. You can verify that. Okay? But as we said, even if these are locally the same, what distinguishes them is the dilaton. Okay? The coordinate rho is different in each of these geometries. If you want to relate the form of ADS with kappa equals plus 1 to the other ones, then you have to change both rho and tau. So then, even if we're using the same letter for rho and tau, they have completely different meaning in the three solutions, which means that also phi has a different meaning. The dilaton has a different meaning in the three solutions. Okay. We said the dilaton blows up at the boundary. And what do we do about it? Well, we introduce a cutoff. So we're saying we introduce a cutoff at a constant value of the dilaton, much larger than 1, okay? At some value of that we're calling rho equals 1 over epsilon. We introduce the renormalized value of the dilaton, phi b, which I'm going to call it, the cutoff. So, introducing the cutoff, we're not in ADS anymore. We're in near ADS2. Okay? So that's why people here refer to near ADS2, near CFT, because this cutoff also breaks conformal symmetry. Okay? So we're not doing properly ADS2, ADS CFT. That's one of the reasons that it took much longer to understand the two-dimensional case of ADS CFT than the higher dimensional ones. It's not exactly, I mean, you're breaking the symmetries. When we introduce the cutoff, then the geometries, these three geometries, they don't describe all of your ADS. So in the case of global, kappa equals plus 1, you're throwing away this region. Okay? You have this boundary here, and then you have this boundary here, and you're preserving this. And the same thing for the other two geometries. You're throwing this away. Throwing this away, and the Poincaré case, same thing. Okay. So we're going to describe the dynamics of these cutoff geometries. Okay. Now you see that here we have this boundary. This boundary is a wall line, so we can think of it as a particle. Okay. So what we're going to do is, because the geometry is fixed. If there's anything dynamical now, it's going to be just the boundary geometry. Now, you realize that when we're introducing this boundary, then this, the position of this boundary here, this is something that becomes normalizable, something that doesn't go to infinity. So I could have fluctuations, finite fluctuations of the boundary of this geometry. Okay? So I can consider now, this is my ADS, I can consider that the boundary is fluctuating. It could be a curve that's fluctuating. Okay? And this is a wall line that's moving in ADS2. What we're going to do is describe the dynamics of this fluctuating boundary. Since I've introduced a cutoff, this is something that has finite dynamics. Okay? And then, well, this particle, in this case, if it moves like this, the particle moves like this, then we say that we're in a black hole, a near-extremal black hole, like if it moves like this. If it's like this, then we say that we're in the Poincaré patch moving, and then this would be in global ADS, a particle moving global ADS. So let's consider the Poincaré patch, because that's where we usually do this Federman-Gran expansion. Yes?
So there you wrote phi equals a rho. A is just
It's
phi
just
b.
a constant. It's something that
Is
I
it
can...
equal to the boundary phi b?
Yeah, that's, yeah, essentially it's going to become the phi b. Yeah. We're going to see what this phi b is in a moment, okay?
Roberto, another
Yes.
thing. So the phi is a function of the radius, so it's a function of the two, so it's a field over ADS2.
In general, the general solution can have here, it can have a dependence on time, and there can be also another dependence on time. And I'm going to describe this in a moment. Okay? So let me consider the ADS2 boundary. I could choose any of the three geometries, but it's convenient to choose this one. Okay? And then I have this dilaton, which is 1 over c. And as I was just saying, in general, I can consider the general solution something that can depend on time. Okay? But, well, I'm not going to do it in this manner. We're going to proceed in a slightly different way. But, so we introduce a boundary. We're going to introduce a boundary. In the way that I've described it, we introduce a boundary at z equals epsilon, and then we define our boundary time to be the coordinate I'm going to call capital T. So the geometry of the boundary this is the induced metric. This will be okay, where epsilon is small. And then T is the proper time, the renormalized proper time of the particle at the boundary. Okay? Now, this is a boundary that I've introduced, as I say, at constant value of z. But in general, I can introduce my boundary and allow for fluctuations of it. Okay? I can make the boundary to be parameterized by a curve that's of this form, but I want to keep HTT to be minus 1 over epsilon squared. Okay. Now, in general, this is going to be, if I substitute this curve here in the geometry, this is the geometry of my boundary, where now I'm allowing it to fluctuate. If I want to satisfy this with epsilon sufficiently small, then this determines that the boundary geometry, curve at the boundary, has to be okay. This term would be a contribution of epsilon squared. You equate this here. This is not c dot. There's no derivative here. This is c squared. So this has to be like 1 over epsilon squared. I'm keeping this, and this fixed. And then my boundary trajectory is going to be of this form. Okay. whereas I say capital T is the normalized proper time. So this is now my boundary curve. I can compute what is the extrinsic curvature, which is essentially the acceleration of the particle. Computing the acceleration of this particle gives me the following. This is boundary geometry. I compute the extrinsic curvature. I expand it for small epsilon, and the expansion of the extrinsic curvature for small epsilon is of this form. Here I get a term that's 1. When I integrate this over the boundary, this is going to give me a very large term. This would be a divergence. So k minus 1 is the thing that eventually will remain finite. So that one over there is cancelled by the one that I introduced here. What is this object here? This is what's called the Schwarzian derivative. Generally that appears all over the place if you're doing things that have SL2R symmetry. Okay. So it's this funny combination of derivatives of the function. So this is a function of t, and dot is the derivative. Okay. So I say this is known as the Schwarzian derivative. This is an object that's invariant under SL2R transformations, meaning that if you change t to at plus b ct plus d, then the Schwarzian derivative doesn't change. These, of course, these are elements of SL2R. Okay. So here what I'm doing is reparameterizations of my boundary. You can think of that. So I have a reparameterization of my boundary, and there's part of these reparameterizations which are not physical because they don't change the Schwarzian, okay, the action. So what is the gravitational action? Now that I can take this, take the equations that I had before and plug it into the action. The gravitational action of my system. The following. So you see that the bulk geometry doesn't have any dynamics. All of the dynamics are at the boundary. Okay? This is because this is a dilaton gravity theory. It doesn't have propagating degrees of freedom. All of the dynamics corresponds to this motion of this particle at the boundary. Okay? It's edge modes, if you want. So I take set R equals to minus 2, because that's what the gravitational equations of motion give me. This is something that I could do also at the quantum level, because phi here appears as a linear field, so I could integrate it in the path integral along an imaginary time direction, an imaginary direction, and the contour along the imaginary axis, and then the integration of this field in the path integral would fix R plus 2 to be 0. So this is something that I get from the classical equations, but it also holds for the full quantum action. So now I take the JT gravity action, evaluate it on cell. Here I have G Newton. For some reason I've introduced G Newton again. This is the term that I had before. Now I replace phi with the renormalized value of the dilaton. And this is the action that I get. And this is finite when I take epsilon to 0. Okay? So there's epsilons that I had here, and the epsilon from the dilaton, they cancel out. Okay? So this is what we call the Schwarzian action. for the boundary particle, or for the boundary degree of freedom. As I said, we've reduced all of the dynamics of our system to the dynamics of a particle moving in ADS2, and the action for this particle is given by this expression. Okay? So all of the dynamics of our system has been reduced to this one-dimensional, at this level still, it's classical mechanics. So we have a classical mechanical system, just 1 degree of freedom, describing all of the dynamics of this, of the entire systems. Okay? Now we're going to use this to do thermodynamics. If you want to let me recap the logic.
Roberto?
Yes.
Sorry, I come back to my question because I didn't understand it. So what happened to the dilaton? In a sense, you had a field living in ADS2.
Yes.
Now all these degrees of freedom disappeared.
So there's no degree of freedom associated to the dilaton. Of course, the dilaton is not dynamical.
Why is not dynamical? So that equation is not a dynamical equation?
Well, I mean, there's no dynamical propagation here. This looks like it's a dynamic propagation. It is not.
It's not.
It is not, because you have here, you have a, it's not like you're going to get a, I mean, it's clear from the action that here you don't have any kinetic term. So there's no dynamics. This is S-wave.
This is because in 2 dimensions, because in 4 dimensions.
2 dimensions.
Okay.
In 4 dimensions, of course, yeah. And
okay.
that's
okay,
it.
sorry, thanks.
But there's no local dynamics. And yeah, one can easily get tricked into the thinking that this is a sort of Klein-Gordon equation in 2 dimensions. It is not. Okay. So just let me recap a little bit of the logic. So we began with 4D Einstein-Maxwell. Then we performed an spherically symmetric S-wave reduction of the system. And then we got a 2D dilaton gravity of a particular kind. Okay. Then from here, we took the near-extremal limit, and then we obtained the 2D dilaton gravity theory became the JT gravity, a particular dilaton gravity theory. As I say, this doesn't have propagating degrees of freedom. We introduce a cutoff, and then the boundary can have dynamics. If you don't introduce the cutoff, then there's, of course, that's not a dynamical mode. It would diverge. But when we introduce the cutoff, then we obtain a Schwarzian theory for 1 degree of freedom. Okay? And now we're going to do thermodynamics. I should be finishing in a moment. If I finish now or if I continue later. Well, I will do it, continue later. Thermodynamics. For thermodynamics, what I'm going to do is, you know that, okay, this is going to be unfortunate, a little bit unfortunate. For the thermodynamics, I'm going to change the boundary time. I'm going to make it a periodic variable, an imaginary variable that I'm going to make it periodic. With periodicity given by inverse of the. So this tau, I had a tau before. That's a little bit unfortunate that I'm using the same letter tau. This tau here before was the near horizon time. Now it's going to become the imaginary time. Okay, so forget about the previous one. Now, from now on, that will be time along the imaginary time direction. I think that most of you are familiar with the idea that if you're going to do thermodynamics, there's this formalism of imaginary time. that thermodynamics means that you're doing quantum field theory in geometries that are extended in the complex time direction, and along the imaginary time direction, you have all of your quantum field theory, all of your correlators are going to be periodic with a periodicity given by the inverse of the temperature. Okay? Beta is going to be 1 over the temperature, and then forget about this T. This T was time. Now it's T. From now on, it's going to be temperature. Okay? Sorry about this. Now, when we go Euclidean, forget about the previous notation. This is going to be our time. This is going to be temperature. Okay? So we'll continue after the break. We'll continue with this. Okay?
Question.
Hello. The Gibbons-Hawking-York boundary term, is it like the unique boundary term you can add?
Sorry?
The Gibbons-Hawking-York term, is it the unique boundary term that you can add to the
Yeah, Gibbons-Hawking-York is, as I say, it's not a counter term, but it's a unique boundary term that you add if you, well, I mean, so Gibbons-Hawking-York gives you a well-defined variational problem. You can add terms that don't modify your equations of motion. Those were like, I mean, terms that don't depend on that only depend on the intrinsic geometry. Those are not going to modify the equations of motion. We use that freedom to add those terms to cancel divergences. So in that sense, Gibbons-Hawking-York, which is not a counter term, is a term that fixes the boundary conditions, the appropriate boundary conditions for a Dirichlet boundary value problem. It's not unique. The non-uniqueness, we use it to cancel divergences.
So the SL2R symmetry that you have in the boundary, what actually happens in the bulk? Does the bulk also have that?
So those are, so this is the geometry, symmetry at the boundary, okay? So in ADS2, you can perform diffeomorphisms. And the diffeomorphisms, usually you would think that they are just, well, gauge symmetries, that they are redundancies. Of course, there's something called large gauge transformations and large diffeomorphisms. There are diffeomorphisms, and the large diffeomorphisms have physical meaning. Okay? These are things that become boundary degrees of freedom, if you want. So there are diffeomorphisms in ADS2 that are generated by vectors that are not normalizable at the boundary, but the metric deformation is normalizable. So these are large diffeos that are dynamical. Now, out of these diffeos, some of them are isometries of the bulk. ADS2 has a group of isometries that are classified by SL2R. So those are not physical. Those are just isometries. Of the diffeos that are normalizable but generated by non-normalizable vectors, those are dynamical. Those are the ones that are captured by the Schwarzian theory. The SL2R of the Schwarzian theory, that corresponds to an SL2R of the bulk that is just isometries. And this will be very important because those are not physical modes, those are not physical deformations, and then we will have to subtract them when we perform an integrate and a path integral over the dynamical degrees of freedom of the system. So those, the SL2R here, as I'm saying, that this corresponds to isometries of the bulk, things that don't change the metric. There are other diffeos that modify the metric, and some of them become dynamical. They are large diffeos. Okay.
Maybe a question related to that. I mean, you said that the dilaton was not a degree of freedom, but it's
not a dynamical degree of freedom, not a propagating degree of freedom.
Okay, I don't understand the difference because the equations were coupled to the stress energy tensor.
Okay.
And it seems to me like you now are translating that dependence to this boundary degree of freedom that is going to be coupled to the stress energy tensor. And why we're not calling
Okay,
that?
so yeah, maybe when I say that it's not a degree of freedom, that's one has to be careful. It's not something that propagates. The reason, so we're considering here gravity, or Einstein-Maxwell, in a spherically symmetric sector, and so we know there are no spherically symmetric propagating waves of the gravitational or the electromagnetic field. This doesn't mean that the theory is completely trivial. We can have different solutions. So we still solve the equations and find different solutions, which are spherically symmetric. Okay, so even if there's nothing that propagates, they are not propagating degrees of freedom, it has a dynamical, or that's, in that sense, there's dynamical information in the sense that you can have different solutions. But the solutions don't, there's no propagation, okay? So it's spherically symmetric, and this corresponds to what you may call breathing modes or breather modes of the geometry, but they are not, they don't give you classical dynamics. So we don't get this theory. The classical dynamics is just corresponds to, well, fixing some particular solutions, like the Reis-Nostrom solution or other solutions with different values of the energy, okay? So you can have different solutions, but as I say, there's no propagation. And when we perform the path integral, what we're going to see, at the quantum level, yeah, you have to integrate over all of the fluctuations, including possible spherically symmetric fluctuations, but at the classical level, they don't give you anything other than some fixed solutions. I don't know if I've replied well enough.
You are thinking like if you expand the dilaton in mode or something like that, there's
no, the dilaton I expanded, so I introduced a cutoff because otherwise my dilaton blows up, so I introduce a cutoff in the dilaton. So that's to make things finite. To make things finite, I introduce this cutoff. This breaks conformal symmetry. This breaks also parts of the symmetries of ADS2. And well, since now the position of the boundary is something that can, I mean, it's a finite distance, it can fluctuate. The fluctuations, as I say, they don't have classical dynamics. Okay? They are going to be, in classical solutions, they are going to be fixed to the solutions that we already discussed. The quantum fluctuations, that's what we want to capture, the quantum fluctuations of the boundary mode. But classically, it's something that it's just fixed. If you couple it to other sources, if you couple it to matter, then yes, then you can have that the boundary can move, responding to what matter you're coupling to the system. And that's something that can be interesting. If you couple this to matter, then the boundary can move even at the classical level, but we're not introducing that coupling to matter here.
Thank you.
Hello. In the action you have taken L is equal to 1.
Yes.
For that R became -2, right? R became -2, your curvature.
So R, yeah, the curvature becomes, so the scalar, yeah, it becomes -2.
Yeah,
yes.
but that could have been like 2 by L square, and then.
It would be 2 by L square. I can restore the units if
yes.
if I want to, yes.
Yeah.
Just so like sometimes in my equations, G Newton appears, sometimes it disappears. It happens all the time.
So now the Euler number that you have written the equation for is integral over this R.
Yeah, so that's,
that might change, and is that related to the...
So, well, I mean, there's something that doesn't change because, I mean, this 2 dimensions, this is, I mean, this has dimensions 1 over length squared, you integrate over 2 directions, so this is invariant under rescalings.
Okay.
Which is consistent.
Okay.
Was that your question?
Yeah, I have...
In other dimensions it wouldn't be, of course, but 2 dimensions is different. I mean, you have the square root of G. This has dimensions of 1 over length square, cancelled out, so it's invariant under rescaling of the coordinates. Okay. So in order to do this, of course, I have to rescale the coordinates, but this doesn't change. This is, anyway.
Okay, so yeah, we're a bit short on time, so unless there is a very urgent question, let's thank Roberto again. We will resume at 11:15.